So yeah, my name is Prokofyev. I'm from University of Fribourg, Switzerland, and I'm going to present you our joint work on grammatical error correction by preposition. Okay, so I start with task overview and motivations for our work. So grammatical error correction is important by itself, of course, but it is also important as a part of machine translation and speech recognition tasks, especially as a part of machine translation, as different prepositions are used. So in different languages, different prepositions are used in the same context. So it is reasonable to correct them. So in our work, particularly, we are addressing the task of correcting errors done by English learners. So this is different, for example, from the task of language disambiguation, where you basically assume that you remove all the prepositions in the text and try, based on the context, to tell what is a preposition. So in our case, we have all the prepositions in the text and we have all the correction. And English learners, so that means there are some percentage of prepositions where they make errors, and usually the quantity is pretty low. Okay, so for example, given a sentence, we have a list of candidate prepositions, of English candidate prepositions, and we're trying to rank them and to select the best one that is suitable for the sentence. So we rank candidate prepositions by their likelihood of being correct in order to potentially replace the original preposition in the sentence. So the grammatical error correction is a quite well-researched area, and a number of approaches have been tried in this area. For example, multi-class classification with predefined candidate set, and also statistical machine translation and language modeling approaches. And basically, the statistical machine translation and language model approaches work by assigning different mobility, basically by trying different prepositions in the sentence, they assign different mobilities to the sentences. It's sort of the overall. And for the classification, for the supervised approaches, a number of features have been tried, such as lexical features and part of speech tags, and also head verb or nouns and different word dependencies inside the sentences, and also n-gram counts from the large corpora, such as Google Web 1T corpus, and of course for the confusion matrix, which is especially important for the English learning task, which gives you the probability of basically of replacing some preposition in the text with a new one. Okay. So the key ideas for our approach is we think that the particular preposition is the usage of a particular preposition is governed by a certain word or an n-gram, and this is not always the case. There are certain special cases. For example, with the pronouns, you need to look at another sentence or something similar. But in many cases, even out the special case, in many cases this is actually true. And so we formulate our task as selecting or aggregating somehow n-grams that influence that preposition usage. And we are going to use the n-gram association measures to score each preposition. So this is the overall processing pipeline of our approach. First do sentence extraction, then go to tokenization phase, the n-gram construction. We generate the list of n-grams for every sentence, and then we basically use n-gram statistics for every n-gram generator rank preposition for every n-gram. And from each stage, we extract different features, which I will talk about later, and then those features are fed into the supervised classifier, and finally the classifier tells what is preposition needs to be substituted or not. Okay, so I start with the tokenization example and how we define the n-gram distance, which will be used further in our work. So basically, we define the n-gram distance as the distance between the preposition and the closest word from an n-gram to the preposition. And if the n-gram is on the left, the distance is negative, and if it's on the right, the distance is positive. And if the preposition is inside the n-gram, which means there are words from the left and from the right side of the preposition, the distance is considered to be 0. 0. And this is a special case also with the central n-grams, which I will talk about later. Okay, so every n-gram, we split the sentence into n-grams. Each n-gram has its own distance. And for every n-gram, using the association measures, we generate a rank list of preposition using the association measures. And we tried in our work a number of association measures, and the best one, we tried the student t-test and the likelihood ratio and pointwise mutual information, and we found that pointwise mutual information suits best for our task. The major drawback of pointwise mutual information is that it's very it's influenced if your data is sparse. Basically, if there are two words that frequently appear together and they only appear together, it tends to give them higher scores. But we're using a very large, we hope that by using a very large corpus, such as Google Books n-gram corpus, we are able to mitigate the data sparsity problem. Another important thing is n-grams with skips. So in our work, we tried the n-grams with determiner skips. So what is it about? We found that around 30% of prepositions are used in the proximity of determiners, such as A and B. And determiners are not really influencing the choice of a preposition. You can see that from the graph, if the correct, which shows the correct preposition ranks from 1 to 49, and for different part of speeches. So we show here the determiners and nouns. And you really see that for determiners, it's the correct preposition rank is really random, which means that the determiners don't know. It's even skewed towards the higher rank. So the determiners don't tell what is the correct preposition. While for the nouns, you can clearly see that the ranks are skewed towards the higher position, which means now nouns have more influence. And by ignoring the determiners, such as, so you see in the example below, one of the most, if we remove the determiner and it becomes one of most, we can easily then calculate the association measures effectively for 4 grams as if it were 5 grams, because it's kind of intractable to calculate the pointwise mutual information and other association measures for any n-grams higher than 3. Okay. So the features that we coming to the features that we designed for our classifiers based on these observations. So first I start with the PMI-based, the association measure-based features. So we designed the following set of features: the average rank of prepositions among the n-grams rank, and the average also the average PMI score of the prepositions, and the total number of occurrences of a certain preposition on the first position of ranking. And you can see everywhere it's among the set of considered n-grams. So why do we do this? Because we think different n-grams with different properties are influencing the sentence, the usage of preposition differently, because I was talking about earlier. And we group n-grams into two. Logical, we export 2 logical groups. First we group by n-gram size, either it's unigram or bigrams or trigrams, and we average those ranks and PMI scores only for unigrams or bigrams, and all those go as features. And second is the n-gram distances. We also average all those scores, the ranks and PMI scores by distances, either it's -1 distance or 0 distance, and for every such distance we have the average of those scores. Another feature is the central n-grams, the n-grams with distance 0. As you can see from the graph that n-grams with distance 0 are really special case among other n-grams, because they tend, so here is a graph that shows the count of the correct prepositions for n-grams with different distances. You can really see that n-grams with distance 0 turn to give the majority of the correct results, which is kind of straightforward because they have the words of the left to right, they have the most influential positions. So it is reasonable to separate the ranks and PMI scores of the central n-grams as a separate feature, and that's what we've done here. Okay, and finally, for preposition selection, we use supervised learning algorithms, and we use a random forest as a classifier, which is a very powerful and versatile classifier. So the whole classification procedure is done as follows. We use a two-class classification with a confidence where we give a confidence score from 0 to 1 for every preposition from the candidates set, which is different. So this is quite different from the previous approaches that used multi-class classification. So we have a different set of feature values for every preposition from our preposition candidate set. And every preposition gets ranked from 0 to 1. And the preposition is determined by basically sorting the prepositions from the candidate set according to the confidence score. Okay? So the training and test collection that we're using, so the training collection that we're using is a standard one. It contains 27,000 sentences, and it is basically a set of exams from Cambridge University, from the first certificate of English of non-English speakers, exams from years 2000 and 2001, and it's pretty large. And the test collections we use, one is a QNLL 2013, which is also test collection done in academic setup. It's 50 essays written by non-native English students from the National University of Singapore. And another new collection that we explore in this work is a Stack Exchange. So you all know the Stack Overflow websites and other set of websites where you post questions and get answers. And it's actually a very interesting website. It provides open source access to the data. And you can also get all the historical data from it. And what we did is we extracted two versions of sentences where the editor put as a comment if he modified either grammar or spelling. And we extracted around 6,000 sentences from this collection, also as our second test set. Okay, the experiments overview refers to check the feature importance score to determine which features are the most influencing. And then we study how the impact of n-gram sizes and distances on the performance of the classifier. And finally, we go to the evaluation on test collections. Okay, so the feature importances are as follows. So the most important feature is confusion matrix probability, and this is not a surprise because in all other works the confusion matrix features got a high score. So why is that? Is that again because we're fixing errors done by English learners, and usually the percentage of errors done by them is quite low. It's around 5 to 10%. So in the 95% of cases, you don't need to correct errors. So the confusion matrix probability basically gives you this probability of whether the preposition should be corrected or not. And what is interesting here is that really that the all other top features, except the confusion matrix, are based on the PMI scores, which means that the association measures really give a performance impact, and they're the most influencing features for the classifier. So you can see average rank, top preposition counts for trigrams, central n-gram rank, and so forth. Okay, so the n-gram sizes and distances experiments. So we first tried to see, we define this n-gram distance as the distance between the word in n-gram closest to the preposition. And we did the different restrictions with considering only central n-grams, the distance -1, 1, -2, 2. Okay, and we found that the best performing distance is from -2 to 2. However, it is not statistically different from the -1, 1, and from others, and from higher results as well. So that means that finally we took only the n-grams with distance -1, 1, as then you don't need to calculate other PMI scores for all the n-grams. So it's just computationally more efficient to consider less n-grams. Then you don't have to do much work. Okay, and then we did the experiments with n-gram sizes. So we considered only bigrams and trigrams, and then only trigrams and skip n-grams, which is effectively tetragrams, and then also all possible n-grams, which is bigrams, trigrams, and tetragrams. And we found that really the addition of those skip n-grams, where we skip the determiners, it really provides, it's 2%, approximately 2% higher in the F-score, and with a statistical significance, which means that the skip n-grams really increase the performance of the classifier. Okay. And finally, the evaluation of the test collection. So we compared with our system with the best performance system as a PointLL challenge on preposition correction. And so our approach was a bit lower in terms of precision, but in terms of recall it was almost 3 times higher than the best performing approach at PointLL, and then it resulted in total the 13% absolute improvement, up to 30% F1 score on the data set. So, and then the second evaluation for the stack exchange data set. So the stack exchange data set, of course, is more challenging since it was not corrected manually by expert. It was corrected by the same users of the Stack Overflow as you and me. Okay, and I think it's harder setup. So the first experiment that we did is that we did the classifier trained on the Cambridge collection exams, and we checked the performance of it on the Stack Exchange collection. You can see we obtained the F1 score of approximately 18%. And the second one we did with cross-validation. We trained on the part of the same Stack Exchange collection, and part of it we used as a validation, and it achieved the F1 score of also approximately 28%, much closer to the evaluation of the PointLL data set. And this means that really the different connection with different quality of content, like the academic and the user-generated content, so they contain really different phrases and they require separate training. Okay, so the main takeaways of my talk is that it's really the association measures for n-gram can improve the performance of a classifier for grammar correction task a lot, and especially if you have a large corpus from which you can leverage those association measures. And also the second thing is that the two-class classification preposition ranking is also allows to get the higher performance results as compared to multi-class classification, which we also tried. And it allows to significantly outperform the state of the art. And the third part is that the skip n-grams also contribute significantly to the final results, and we think to consider to kind of skip or consider to skip either different part of speeches, not only the determiners but some other features, and think how this, but this is of course require more care than the determiners, which are not influencing positions at all. Okay, so thank you for your attention.
Thank you. Any questions? So you showed interesting improvements over what was the state of the art, but still F scores of F1 scores of 0.3 are leave some work to be done.
Exactly.
So what sort of mistakes did you run into?
So that's a bit of a problem that, so we use the metrics that were designed for this task to fairly compare with it. So I think it's a bit the problem also of the metrics, because the metrics depends highly on the percentage of errors that English learners make. So if your error is lower, your performance results will always be lower, and if your error rate is like 50%, the metric will be higher, because the system gives sometimes corrections for the cases where the corrections doesn't need to be done, and this degrades the performance results a lot. But if you come to the errors that the classifier made, that you can say that the major problem is that still the data is quite sparse. So again, need to either somehow skip the n-grams to check what other words. So basically there are not enough n-grams in the dataset. There are still n-grams with 0 counts, and you cannot determine anything if you don't have the n-gram. So you need to apply some tricks.
So how large was the variance in the, for instance, in the stack exchange case where you did, what was it, 5-fold cross-validation? Tenfold?
It was so it's in the paper. I don't remember also. I think it was 5 or 10-fold. But the variance was around 1-2%. I think. I didn't put it here, but I can look it up.
Okay, well, the difference between training on the acreage set and training on stack exchange was quite big, so I expected the variance to be a bit larger.
Yeah.
Okay. Anyone else? Yes, please.
Probably I missed it. What is the percentage of mistake in first data sets, which is like, as I understood, for people who already have some English level, and for the stack exchange? Basically, why I'm asking, because if you kind of going to pass some exams, you're probably already kind of prepared, and so basically you expect people with the same level, and in stack exchange, the people are completely with different levels of the English. Did you see something like that in data, and probably it can help?
Yeah, I didn't put this slide for the sake of time, but here it is. So the percentage of errors within Cornell and Cambridge is actually quite similar. It's around 5%, and in Stack Exchange it's much higher. It's 38%. But like this is clearly explainable because we took only the sentences that contain errors. Why we did this? Because we don't know if anyone looked at other sentences that didn't contain errors. But of course, for the experiments, we resampled the Stack Exchange collection as if like the error rate was also 5% as in other collections.
Yeah, I think it makes sense. Also, if I will think about myself, so I better check myself before posting something online. So I don't know, using some techniques like that. Probably people check themselves before doing some.
All right. So this is the end of the session. Let's thank Roman and the other speakers again.